Ladies and gentlemen, please welcome to the second day of Fracture Mechanics Summer School. I would like to invite our lecturer, Professor B Blackman, to present here his lecture, Deformation and Fracture of Polymers and Composites. Please, Mr. Bumper.
Thank you. Well, good morning and thank you everyone. I'm impressed by the turnout so early on a Sunday morning. Thank you for coming. Thank you for the invitation and the introduction. I'm from Imperial College London. I'm a reader in the mechanics of materials, working mainly with polymers, composites and adhesives. And I've had a fairly long association with ESIS through the technical committee ESIS TC4. I'll say a little bit more about that in the presentation because last year I took over as co-chair with Andy Brunner from EMPA in Switzerland, and we have quite a wide-ranging and exciting range of research activities within the committee, so there may be opportunities for some of you to get involved. So what I want to talk about today is specifically related to polymers and composites, and it's quite interesting just to find out now how many of you are involved specifically with polymers and composites. Okay, so keep your hands up for a moment because I have to. Okay, as I suspect, that's a relatively small proportion of you actually. So it still seems that the metals seem to dominate what's happening. Okay, and that does have a relevance to what I'm talking about here because lots of what's happened in the understanding and the development of fraction mechanics for polymers and composites has followed the metals field. And metals has been the sort of the starting point, and the work on polymers has been to first of all adopt what has happened in the metals field and then to work out what needs changing, because obviously there are specific differences between polymers and metals which make their mechanical response and many aspects of the fracture different. So that's going to be something hopefully will come across in the next couple of hours. Well, I've been asked to compress slightly because of our late start, so forgive me if I'm rushed in places. So the basic plan is to spend the first part of the talk talking about polymer fracture, and then the second part of the talk talking about composite fracture. Okay, there's going to be a small break in between. So I first of all just want to say a few words of introduction to introduce my topic and to say a little bit more about the technical committee that I represent in ESIS, which is TC4. So now you've probably seen this slide yesterday. I suspect that Francesco has talked to you about the modes of fracture, and you're all very familiar with mode 1, mode 2 and mode 3. So what I just want to ask you and pose this question, just to see how awake we are at this time of morning, is when I'm talking about polymers, I'm going to be talking specifically about mode 1. And when I'm talking about composites, I'm going to be talking about mode 1, mode 2, and mixes of mode 1 and mode 2. So my question, just to see whether we're awake, and check whether I'm awake as well, of course, is why is that? Why don't we worry so much about mode 2 fracture in polymers? Anyone want to suggest a reason? So yes, they're isotropic. And why does that mean that we don't have mode 2 fracture in polymers? Yeah.
Combination of the fibers between the batteries and the fibers.
Okay, and that does what? Okay. Yeah. Okay. So I think we're there really. So of course the issue is with and this will be the same with metals of course. But if you have an isotropic homogeneous material and you try and apply, for example, mode 2 stresses at the crack tip, the crack will deviate. Okay, and the crack will try and run locally under mode 1. So therefore we don't tend to try and measure mode 2 so much. But of course in composite materials where you have the constraint of fibers, and in, for example, another big area, say laminated and bonded materials where you have interfaces, you have directional constraints of the crack, and therefore mode 2 can be a very important issue. So when we're talking about composites and we're talking about adhesive joints and laminates, we're interested very much in mode 2 and mixes of mode 1 and mode 2. When we're talking about polymers, we're not so interested. So most of what you hear with the polymer field will be referring to mode 1 fracture. And if we just think about fracture generically for a moment, if we have an isotropic, say, homogeneous material, and we're looking at conventional fracture, we can think of it in terms of a block of the material with a crack introduced at one side. And then we think about the crack growing, and we think about what's happening at the tip of that crack, and we think about the damage zone. In that case, it's essentially a plastic zone with a zone of yielded material. Of course, we move to composite materials and we start off with, say, short fiber composite materials. We have a more complicated picture, and rather than just a plastic zone, we have a damage zone, because we have a situation at the crack tip where not just plasticity is occurring, but of course we can have multiple additional damage mechanisms introduced by the fibers. So this might be, for example, fiber matrix debonding. It might be fiber fracture. And there are other things that have been going on there. So we have a more complicated picture with a composite material than we have with a straightforward polymer. And you can see there in the inset, we make the distinction between the damage zone and the plastic zone. And of course, one would expect, and one of the reasons we put those fibers in is to increase the size of that zone and to dissipate more energy. Moving to laminates, where we have, for example, layers of fibers embedded into a matrix, in this case an epoxy matrix, then of course if we introduce a sharp crack and we try and run a crack through that material, we know from what we know about the mechanical properties of fibers is that the fibers are not going to tend to fracture. In fact, it's relatively difficult to get that specimen to transverse fracture. Relatively complex geometries are required to force transverse fracture across the fiber layer. So we have to, in this case, what will tend to happen is the fiber will tend to run in between the fibers, and we'll get in that what we describe as a lateral splitting, which we determine as delamination. So when we talk about composite materials, what we're very interested in is indeed what's actually happening between the layers of fibers, and this weak interlaminar layer where we're actually getting cracks propagating at relatively low amounts of applied energy. So in terms of the composite fracture mechanics, we're very interested in what's happening between the fibers, and in polymer fracture mechanics, obviously we're interested in what's happening in the plastic zone and or a damage zone. I'll say a little bit about the technical committee that I'm involved with. So I mentioned ESIS TC4. So ESIS TC4, so those of you not so familiar with ESIS, it has a relatively large number of different technical committees looking at different ranges. Now, you make different aspects of structural integrity. So I suspect, did you have an overview of that yesterday? Not really, okay. Well, I'm not going to give you a major overview, but there are something like 17 different TCs, different technical committees, looking at, for example, TC1, the very first one to be developed was elastic plastic fracture mechanics. There's one on fatigue and micromechanisms. There's a TC on concrete. TC4 is polymers and composites, and there are some new TCs just developed since the last main meeting, dealing with aspects such as finite fracture mechanics and non-destructive evaluation. The TC4 looks at fracture in polymers, composites and adhesives. And it was set up originally by Gordon Williams and Henning Kausch, and then it was taken over. Henning Kausch retired, and Andrea Pavan from Politecnico Milano took over with Gordon Williams. And the idea really was to explore different ways of using fracture mechanics to investigate polymers and composites. So to foster fracture mechanics methods in polymers and composites, to develop fracture mechanics-based test methods and to use those in design. Okay, so that was always a more difficult thing. I mean, we know that there's not so much use of fracture mechanics in design. We always try and promote this. Industry is still quite conservative in what it will accept, and those methods which are traditional and well understood tend to still dominate. But fracture mechanics has been coming up and has been providing different tools for designers, and I think increasingly this is becoming mainstream. To achieve these aims, then, we basically identify an area where there's a requirement for fracture mechanics to be used to understand the problem. Whenever we do that, we identify a topic, and then we require a topic leader. And the idea then is to develop a fracture mechanics-based standard to understand that topic. And this usually involves a large number of different collaborators. So we set up things called round-robin activities, where a particular test protocol is first of all written down. So someone says, this is how we're going to do this particular test, and we have a number of participants. So the proof of the pudding is always in the eating here. So you have a batch of material and you send it around to, say, 10 different labs, and they all perform the tests according to the protocol, and you get the information back, and you see whether or not A, it's correct, and B, is it repeatable, and C, is it reproducible. For any standard, you have to have accuracy, you have to have repeatability, and you have to have reproducibility. So there's no point with the same method being used in the UK, getting a result, but when it's tested in Italy, we get a completely different answer. That's nonsense. So it has to be unified, and we have to get the same results from using the same method, provided the protocol is followed. To effect that, we have 2 meetings a year. So if any of you are involved in or would like to explore and what you might potentially want to contribute to such an activity, let me know, and I can tell you when the next meetings are, for example. So to give you a bit of an overview of what TC4 has been doing in terms of polymers, composites and adhesives, I'll talk specifically about the polymers to start with, then composites, and then briefly adhesives. So in terms of polymers, we have a number of different ways of if you like, evaluating fracture in a polymer. So of course, there are the linear elastic methods. So when we have overall LEFM behavior, then we can apply LEFM to identify the fracture parameters K and G. So the left-hand column of this table that you're looking at really are the LEFM methods. So the initial ones were to determine a K1C parameter and a G1C parameter using a quasi-static method. That method was standardized in 2000, is really the bedrock, I would say, of polymer fracture testing. So whenever anyone is evaluating a new polymer, almost invariably they'll start with that methodology. Of course, that can be developed to, for example, to deal with rate effects. There's a great interest in whether polymer fracture is rate sensitive. Now, of course, with polymers it is. Polymers are very rate and temperature sensitive materials, so if we are thinking about the difference between a quasi-static test and a test at, for example, a loading rate of 1 meter per second, where the time to failure may be of the order of milliseconds, that's going to be a significant effect in a polymer. So the standardization of that test at higher rates has been an issue, and you can go, of course, even higher than that, and that's been an activity. Looking down the right-hand side of this column, you see the elastic plastic fracture mechanics area. So this is where the LEFM methods are not holding. We have substantial plasticity and non-linearity, and therefore we need different methods. So the LEFM methods become invalid, and we have a J1C. It's not a standard, it's a protocol, because there have been significant issues with applying the J1C method in polymers. It's been a major work area within TC4, and a great difficulty has been really controlling the amount of crack growth that you can actually achieve in that sort of test. I'll talk mainly in this first section about LEFM, but I'll make some reference to the difficulties we're having applying the J technique to polymers. So it's still very much the right-hand column there, still very much a work in progress. There's an an elastic plastic fraction mechanics method for polymer films, which you see in the bottom right-hand corner there, based upon the essential work of fracture. Now, this is a variant of J, but it's for a plane stress condition, so it's basically applied to polymer films. It's a double-edge notched specimen, thin film. The idea is to generate a complete plastically deformed ligament in the center of the material and effectively measure how much energy is dissipated by growing the crack from the edges through to the center. Again, that's a method that is intrinsically quite simple, but has been enormously difficult to obtain reproducibility between different labs. So the technical committee has been working on that method for in excess of 10 years, trying to evaluate why that reproducibility is not there. Down the center, this is a mix. You can have situations where LEFM applied, for example, in tension fatigue. Situations where sometimes it does, sometimes it doesn't in terms of the environmental effects. And a method, the bottom center, you can see a cutting method. I'm going to say a little bit more about it in this talk. So the idea is that sometimes if you can't apply LEFM to a polymer specimen and you want to avoid the complexities of J, sometimes you can use a cutting approach. So with a cutting approach, what you're doing is you're removing a thin strip of the material and you're trying to determine the energy required to do that, and if you plastically correct that, you can end up with a term which we correlate to GC. So I'll say a little bit more about that later on. Moving to composites, then with composites we've been, for the reasons we discussed a little bit before, we're interested in mode 1 and mode 2, and of course mixes of 1 and 2. You might ask about mode 3, so of course there is some work going on mode 3. It's an area that the technical committee haven't got specifically involved in yet, so we've been mainly involved in matters of mixes of mode 1 and 2. But of course, with those mode mixes, you can have the quasi-static situation where the crack is loaded slowly. You can have the fatigue situation. So we've been looking at developing fatigue protocols, and of course the high rate situation where you have a rapidly growing crack. So in that case, the fatigue and the high rate are all work areas. Now the ones that have been highlighted in yellow are ones where we actually have international standards have been developed as a result of not always entirely ESIS TC4 activities, because obviously for international standardization, sometimes you need, for example, ASTM to also agree, although ASTM, of course, have their own range of standards, and, of course, groups like the Japanese group and European. But ISO standards are the goal, usually, of what this particular technical committee is trying to develop. Just very briefly with adhesive joints, I'm not specifically talking about adhesives this morning, but of course many of the things that we say about a composite material also are relevant to an adhesive joint, because we're talking about a laminate. Typically with a structural adhesive, for example, we're talking about a thin adhesive layer between two rigid substrates. So that has a lot of analogies to a composite where you have a matrix and you have rigid fibers. So it tends to follow the same basic trend as the activity for composites. So I'm going to start off with just talking a little bit about the basic quasi-static test method for polymers. And I'm going to talk about some of the unresolved issues that are still actually dogging this methodology. So those of you who are working in this area might be surprised that this isn't all done and dusted, okay? Because the basic method was standardized in 2000, okay? So the preliminary research was done in the 1990s, okay? But still there are problems with this methodology. And I want to just flag up what some of those problems are and what's happening about them before I go on and talk about one of the newer techniques. So let's just talk about polymers for a moment. So most of you, I think we've established, are either working on metals or you're working on non-polymer systems. So of course, when we're talking about polymers, we're talking about a very wide range of materials. Okay, so they are enormously diverse in their properties and their applications. So from the rigid side, we have rigid thermosets, epoxies, and these sorts of things that are used as matrices for composite materials. And of course, to the other end, we have elastomers and gels. So we have very, very soft, very compliant materials would have been used in increasingly in biomedical engineering, etc. So it's an enormous range, and therefore it's not going to be the case that any one particular method will be suitable for any more than a very small subset of these materials. So I think that's an important point to start off with. And the second thing is often we're talking about tough and ductile. So we're talking about brittle, we're talking about ductile. And it's best with polymers not to think of those as a material descriptor. So best not to think about a polymer being tough or a polymer being brittle, because under certain conditions, pretty much any polymer can be either, okay, depending upon, for example, temperature and rate of loading. So it's best not to think of a polymer as being tough. A polymer can be tough under certain conditions. So it's better to look at the conditions. How else is a polymer different from metal in terms of fracture? Well, the main things are time and temperature sensitivity, so much more time and temperature sensitive than metals. And secondly, they can be very notch sensitive. So we have to worry intensely about the situation of the initial notch. This has a big implication on the results that we always obtain from these standard methods. So just thinking about going down that left-hand column of my diagram, we're looking at linear elastic fracture mechanics here, where we're using LEFM to characterize fracture either via the K parameter or the G parameter. So stress intensity factor or energy release rate. When we move to composite materials, then there is a preference in much of what we do to use the energy release rate parameter. And that's to avoid many of the complexities that we have when we have nearby interfaces. Okay, so we all know that we have problems with the K field and the definition of K close to an interface. Now, Professor Banks-Sills is going to be talking specifically about interfacial fracture after me. Okay, so I don't want to say too much more about interfacial fracture, but from a perspective of what we do in TC4, we tend to focus, when we're talking about composites, on the G methods. However, for polymers, in this context, we're following a metals approach, and K is defined first, and then from that we define G. Of course, if we're using LEFM, we're basically assuming that we have linear elastic behavior of the specimen. The crack tip is in a state of plane strain, and the crack should be sufficiently sharp to ensure that a minimum toughness is obtained. Now, this is a really big issue. Okay, so how sharp should a crack be, and how sharp is sharp enough? Okay, so this is a point that we've debated at very great lengths, and it gets a little bit philosophical at times, because there is an argument that if you just keep making a crack sharper and sharper, you get a lower and lower toughness. But of course that has a major implication for the use of fracture mechanics. So the basic idea is that there should be some sharpness where if you make it any sharper, you don't get any lower value of fracture resistance. So there is some value there that we always try to obtain in our fracture testing, where we say we have a full state of plane strain, and our crack is giving us this lower bound value that we can go away and use in confidence. Okay. Now, as I say, it's slightly controversial, but we do hold by that principle. So in basic, we're starting off with the metals method, which was ASTM E399. So those of you more metals-based will be familiar with that. And that was used as the basis for the polymer fracture test. And of course, then the idea was to modify that based upon what we know about polymeric materials. So the fracture specimens are relatively familiar. We use a single edge notched bend specimen or a compact tension specimen. So we favour these specimens because the stresses are essentially bending stresses, so we can satisfy our plane strain conditions for minimum size requirements. So we have reasonably compact specimens. Of course, we For a polymer, we're usually moulding sheets of material, so these might be injection moulded or they might be extruded and cast. But normally we'd set the thickness of the plate to be the thickness B of our specimen. And then we'd machine those specimens out. So we'd set an initial crack length. So if we normalise that crack length with the width of the specimen A upon W, we're looking for a A upon W ratio of about 0.45 to 0.55 to start our specimen off. And we start off making the specimen with typically a width W of about 2 times the thickness, and we can move from there. So that's usually the starting point. Right, so notching, and I've said this has been a major issue for polymers. So what about the notching? So what I've said before is that the aim of the notching is to create a natural crack. So what do we mean by a natural crack? What would a natural crack look like if we found one in the material? Well, this is what we're trying to create. We'll look at whether we've done it in a moment. So the metals community solve this problem typically by milling in a notch and then using fatigue pre-cracking. Quite an effective method, generated sharp cracks. Additional problems for polymers, though, is we have thermal problems in polymers. Okay, so if we use a fatigue pre-cracking method, we can introduce thermal damage. So that's one problem. The second problem, of course, it is a complication. It's just that it's more inconvenient to have to do a fatigue test prior to a quasi-static test. So there are some issues there. But what we did as a technical committee when developing this method was to first of all create a machine notch in the same way as the metals community did, and then extend it by, of course you can't do this for metals, but with polymers you can use razor blades and you can tap razor blades into the milled notch. So that was a very popular initial way of doing it. I put cold in brackets there because whenever you talk to any of our PhD students who are doing this, they always say, well, we always take our razor blade and we freeze it in liquid nitrogen first. So you have a very cold blade. Okay, that's not actually in the standard, but it's a very practical way of meaning that the material right at the crack tip is cold without introducing brittle behavior in the rest of the material. Of course, if you put the whole block of polymer in liquid nitrogen and then razor tap it, it's going to be brittle fracture almost certainly, and you have no specimen to test. Okay? So most of people who use this technique use cold razor tapping. The idea with the cold razor tapping is that what you're trying to do is you're trying to put this natural crack into the material, and you're trying to get it away from the tip of the razor blade such that you extend the crack, and the rule of thumb here, the crack extension should be about 4 times the machined notch tip radius. So you get away from the influence of what the milling machine has done. And that's fine, of course, provided when you put your notch into the specimen and you tap on it, it's fine provided this is what happened, you get this nice crack growing off. There are difficulties with it, and we'll look at those next. If, however, you can't do that and you tap on your razor and nothing happens, which is what happens with many polymers, then of course all you're doing is introducing residual stresses beneath the razor blade. Okay, and residual stresses of course will affect the fracture parameter that you measure, so you want to avoid residual stress. So the method that went into the standard was to use razor sliding. So if you can't tap a crack, you slide a razor blade across the machined notch. And there are many problems with that technique as well. So people who do that find that you draw a new razor blade across a crack and you look and you can't see that you've done anything. So typically there's a tendency to want to do it several times. So we have students in the lab, they do it again and again, and you actually look under the microscope and then you've got multiple slashes across the crack tip. And which one then initiates is always an interesting thing to see. But there are issues here. So with the razor tapping, it's difficult to control the crack length because this is an unstable fracture process. You're simply tapping and the crack will run, but it won't necessarily run straight and it won't necessarily run the length that you want it to run. We talked about residual stresses because we're hitting a blade into a material, and we're talking about, we've mentioned this multiple crack problem that we have. So here are 2 diagrams of 2 notches that were razor tapped. A student working with me use, for example, we see on the left-hand side, you've got a SAN polymer, so styrene acrylonitrile. And there you've got the milled notch at the top, so you can see, and then what the student has done is that you put a razor blade in and tapped on that and generated this crack. So hopefully you can see, I'm sure I can, okay, so apologies to the people on this side of the room, but there you can see the natural crack coming down to the bottom, natural crack coming down to the bottom. What you can see about this crack is it's very sharp. We think about the notch tip radius down there, it's going to be very sharp, so very sharp crack, but the problem is that we haven't been able to control necessarily the length of it, we haven't been able to control the direction of it. And that's also been the case with the epoxy specimen here. There you can see our initial milled crack, and then there's our razor tapped crack. So that's an issue there. And what happens for all the materials that we can't do this to? So these materials that are tougher, under the conditions that we're investigating, and we simply tap on the crack and nothing happens. So it's unsatisfactory, and this was becoming increasingly apparent as people were testing a wider range of polymer materials. The methodology was fine, but you couldn't get the cracks into the material in the first place. So we had quite a substantial look at this problem with a number of labs taking part. There are a range of academic labs, universities, and industry. So BASF in Germany also took a major lead in this area, with a number of people working through TC4. So the basic problem was that we couldn't actually use this methodology to get reliable, consistent fracture data for polymers. So the question was what to do about this initial cracking problem. And what we did was obviously had a look at different methods. Now, think about what the standard tells you to do. The standard says you can either use a razor tapping technique if the material is going to behave in a brittle manner, or you can use a razor sliding technique if the material is going to behave in a more ductile manner. We've looked at the problems there. There was some interesting work on using femto lasers to generate these cracks. This was some work that was done at Catalonia in Spain, and the femto laser notching was used, and initially this looked really exciting. Apart from being an incredibly expensive method, I think it cost €50 per sample, which choked most of us, but it looked initially very encouraging that we could all invest in femto lasers to make these notches. Unfortunately, then came apparent that actually these weren't, although they were quite sharp, there was a problem with them, and there had been thermal damage to these crack tips. So even these incredibly fast lasers were damaging the polymer. So we needed another approach to this. So we looked at the technique called broaching. Now, some of you may be familiar with broaching, but probably most of you aren't. A broaching tool is a little bit like a saw blade with lots of teeth. But the idea of a broaching tool is that the teeth get incrementally longer as you go down, so each tooth takes a slightly larger amount of the sample away. So it's an incremental cutting process. Now, of course, you can use broaching tools, but the method that we've been looking at within the committee is a different way of applying the same thing. We have a sharp blade. So we've been using blades that are commercially available. So these are like Stanley blades that you put in Stanley knives. So these box cutter type knives for general purpose. So you can buy these knives, and the idea is then to modify the knife and to connect it to for example, a microtome, and to use this in a broaching process. That's what we've been doing. So the key idea of the broaching is that you control the sharpness by controlling the tool. You control the direction and length by controlling the motion of the tool during the process, and you completely eliminate residual stresses. Now, the reason you eliminate residual stresses is that this is a material removal process. It's a cutting process. And what you're doing is each time you're taking a pass, you're cutting the material. You're removing that piece of material that may have been modified by the presence of the blade. So the basic idea is we take our blade, we cut the end of the blade off. Okay, now why do we cut the end of the blade off? The problem if you don't cut the end of the blade off is the end of the blade is too compliant. Okay, everything tapers down to a point. So it's too compliant. So what we do is we remove the end to make the blade less compliant. So it's stiffer, but we retain the notch at the bottom of the blade. That's connected to a microtome, and then what we do is systematically pull this modified blade down across the specimen, incrementally increasing the depth of the crack. So this was some notching, this was some broaching performed by a student in our lab, and you can see this was the milled notch, and then this is the broached notch. And you can see the broach notch, this has been made by incrementally taking this blade and working it into the material. So you can almost see the steps on this process. And she's got down, in this case, to a notch tip radius of about 2 microns. And the nice thing about that radius is that we can measure it, we know exactly what it is, we can control the depth of that, and we can control the direction of it. And we think there are no residual stresses underneath. So, somewhat modest investment is required here, but it's not anything like the scale of required for the femto laser approach, and we can put these notches into to any material in principle. So we haven't yet convinced those people who only work on brittle materials, so those people only working on epoxies still like their razor tapping, but this can be used right the way across the spectrum for introducing the cracks. We're quite excited about this technique. Quite a lot of data's coming along. So let's just have a quick review as to what we do with this information. So, of course, we apply SCNB or compact tension specimen. We load quasi-statically. The rate is specified. We run that until the crack initiates and the forces tail off. The specimen should initially be linear, and then we have non-linearity, a maximum force, and we control the amount of non-linearity allowed in the specimen. So this allows us a non-linearity of about 10% in total. So where does the non-linearity come from? So it could be non-linear elasticity of the specimen. Okay, it could be general viscoelasticity, or it could be plasticity at the crack tip, or it could be, of course, initial crack tip growth prior to catastrophic fracture. So there are a number of sources of this, any initial non-linearity. But what we do is we pick out our maximum force and our 5% force here, and it's that 5% force, provided it occurs before the maximum load point, we use for the data analysis. So that's totally standard and taken from the metals approach. A complexity with polymers, of course, is that they are generally much softer than a metal. So we have to worry more about indentation. So when we're loading these, for example, on the 3-point bend rig, then the indenters may indent quite significantly into the polymer material. So we have to correct for that indentation, and of course we always have to correct for any compliance effects in the test machine. So we have a simple routine built into the standard which basically says that you perform a calibration with, for example, the loading rollers pushed together, so no crack involved, and all you're measuring here is the indentation of the loading rollers into the specimen and the specimen compliance. So you have a way of correcting the data. An important thing to do, because polymers are viscoelastic, we do this at a fixed rate, such that the total test time is the same as you obtain in the fracture test. So the rate is equivalent, and we do these corrections at the correct rate. So we have curve 1, this one on the left, which is our test result. We have our correction curve from our indentation test there, and then we have a corrected curve where we subtract one from the other to give us our modified displacement versus force profile for the corrected experiment. You may be familiar with this. What we then do is we compute a provisional value of K based upon our standard fracture mechanics parameters, an analysis using methods that you probably heard described yesterday. We check for a size requirement, and if the size requirement is satisfied, we then call that our K1C value. What are the size criteria? Well, of course, we have to check that our critical dimensions in the specimen, A, B, and the ligament length, W minus A, all are greater than this 2.5 provisional KQ over sigma Y all squared. So we check that, that's the size requirement. If that's satisfied, this ensures the plane strain condition, and this condition here ensures that we avoid excessive plasticity in the ligament of the specimen. So that's our standard approach for K. And of course for G, this is an important aspect for us, particularly when we're looking at also different and modified materials, but we always calculate the energy parameter. Of course, what we need is the corrected energy, as we see here. So we have the corrected energy. We go through our size criteria, and we determine a G1C value. So that's really the standard methodology. The main complication for us has been the initial condition. So if you're performing these experiments, we would advise you to look carefully at the initial crack that you're putting in. Of course, everything is very, very sensitive to that initial crack. All you're measuring is this 5% offset value of force displacement, and that's critically dependent upon the initial condition. Okay, now I just want to mention that at this stage, of course, we have a relatively wide range of materials that won't pass these conditions. Okay, so for example, either the linearity condition won't be passed, despite our best efforts, or the plane stress, plane strain criteria won't be passed. So we need other ways of evaluating. I'm not going to say so much about the J methods this presentation. There's going to be a lot of discussion of J, the J integral, and the concepts at this meeting. Of course, we're honouring the great achievements of Jim Rice, and of course, there's great potential for this method to be developed to work successfully for polymers. At the present stage, we don't have a completely well-working protocol available for J. Just really as an aside, the main problems we've had with adopting what we describe as a multi-specimen approach to measuring J1C in polymers is controlling the level of crack growth required. So of course you have to put a notch in. The initial conditions of the notch may not be so critical because you're assuming that there will be plasticity. But what is absolutely critical is that you can control a certain amount of crack growth. So in a multiple specimen approach, for example, you would try to achieve different levels of crack growth. And we're talking relatively small levels. So you might have a specimen where you load and try and achieve 0.1 millimetre of crack growth, 0.2, 0.3, up to maybe 2 or 3 millimetres. And our ability to precisely control that amount of crack growth and develop the JR technique is sort of, at the moment for us, the limiting stage. We found it very difficult to get that complete control. So it's very much still an area that the technical committee is working on. There's some very good work going on, for example, Francesco Baldi in Italy, working on this and using things like load separation criteria to try and get a better physical understanding about what polymers will and won't pass LEFM fracture conditions, which will be suitable for LEFM and which will be suitable for example, for J testing a priori. So before you start having a relatively simple test method, it'll tell you where you are in the whole range of validity. So that's really something that's going on at the moment. Just to finish off the polymer part of this talk, I just want to say a few words about the cutting technique. So we talked about broaching, and I said broaching is a form of cutting, but of course we can use cutting to also determine a fracture parameter. So this has been slightly controversial. Of course, again, this is an area where metals, obviously, and the machining of metals has been going on for considerably longer than the machining of polymers. And there's been a lot of work on machining in metals and trying to understand what's happening in a metal, why is the chip behaving in the way that it is behaving, what's happening at the tip of the machine tool, and how do you get a fracture parameter out of that. So what happened with the metals work was that fracture toughness essentially was ignored. They said what we have is a material, and we're going to try and take a tool and machine a thin strip of the material away from the bulk, and we're going to measure the forces involved in that and work out how much energy is involved. And what the people who were working on the metal cutting originally said, well, the fracture toughness of metal is low compared to the energy dissipated plastically during the process, and therefore we'll ignore the fracture toughness term. And Tony Atkins, relatively recently in the UK, commented that actually the flaw in that technique was that the fracture toughness that they were considering was not the true fracture toughness, but was the surface work. So it was more akin to the surface energy rather than the fracture toughness. And of course, we all know that the fracture toughness is different from the surface energy because of what is being dissipated plastically at the crack tip. So therefore, it was an incorrect assumption just to ignore fracture toughness. It's an important point. So Tony Atkins put fracture toughness into metal cutting, and it was an obvious extension then to put fracture toughness, in our case G, into metal cutting, and to see whether that could then be used as a way of extracting G rather than it being an input parameter. So this was something that we explored at Imperial College. So the basic reason for doing this is that we have many polymers that do fail the LEFM criteria. And I've talked about the complications we have currently with applying the J approach. So could we use this technique? So the schematic shows what's going on. So this wouldn't be so different from a metal to a polymer, but you can see the idea here is that we have a block of polymer material. So this is our specimen. And what we're doing in this cutting process is we take a sharp tool. So the tool is shown hatched in the diagram here. And what's happening is that we apply the tool across the workpiece and we remove a slice. An interesting feature here is that you cut, for example, a slice of thickness H, and you get a chip formed. And the chip is thicker than the original slice. So what's happening at the tip here is that we have a shear plane. So there's a plane of material which is plastically deforming. So as this chip is removed from the material, it tends to curl around actually for various reasons. It doesn't tend to come straight up the tool, it tends to curl around. And you can get interesting parameters actually by measuring the curl. Okay? But what's happening is you've got a shear plane, and the material is plastically deforming here, and this leads to a thicker offcut. You need to calibrate or instrument your tool. So in this case, you connect your cutting tool to a 2 or 3 axis load cell. So we used a 3-axis load cell but used 2 axes on it, measuring the force in the cutting direction and the force in the transverse direction to that. So that's an important thing to do. So we have a transverse and a cutting force. And a good way of doing these experiments is to vary the depth of cut. So what we do, for example, is to vary H. So you might have a minimum H of about, I don't know, depends what you can manage with your system, but in our case it was about 25 microns. So we cut a slice about 25 microns off, and we systematically increased that thickness, maybe a factor of 10 or 20 to up to about 0.5 millimeter. And of course the idea, the basic idea really, is that the plasticity in this point here is a function of the thickness. And in principle, if you can reduce the thickness to 0, you have no plasticity, but you generate the new fracture surface. Okay? So if you develop curves where you're plotting, effectively you're plotting your energy against thickness, you can extrapolate back to 0 thickness and determine a value for energy release rate based upon no plasticity in this point here. Now, there are different types of tool. One important aspect of the tool is the rake angle. So it's the angle which the tool leans back from the vertical. So that rake angle can be varied. And typically you have a clearance angle at the bottom because you want to reduce the friction on the workpiece. So typically you have maybe a 5 to 10 degree angle here. But of course in this case you can see that because of the basic geometry, the tool actually touches the crack tip. So this is interesting because you can then think of the energy release rate or fracture parameter as being akin to a force holding the crack back. So you can do this analysis either using equilibrium. So you can solve the equilibrium either on the shear plane or you can solve equilibrium on the cutting tool, or you can use an energy approach. And you can just look at the energies during this steady state cutting process. So it is a steady state analysis, and what we're doing is we're trying to get over the initial sort of bumping around that you'll always get, and then drive the tool in a steady state way through the material. So in this crack tip touching case, we've got this, if you like, this notional force that's holding the crack back. Now, there are lots of different ways that you can analyse this problem. We talked about equilibrium, we talked about energy methods, but all of them tend to require that you measure the cutting force, normalised by the width of the specimen, and the transverse force, normalised by the width of the specimen, as a function of the cut thickness. And there are two ways that you can then proceed. You can either go and find the chip and measure the cut thickness, HC, okay, which is it's good if you've got a careful student. Sometimes it's difficult to find the chips after they usually spiral off, and sometimes they ping and you have to go and find them. So there's a problem with chip identification sometimes, but if you can go and find the chip, you can measure it. So we had a nice case where we had the whole test matrix and we had all the different chips put on a board, and you can see the radius of curvature changed as a function of the parameters of the conditions. So you can do that, you can measure the chip thickness, or you can say, well, what's going to happen is that the shear plane is going to form on an angle which minimises the cutting force. It's like an energy minimization requirement. So that concept was used by Merchant in his initial cutting analysis for metals. We used it and found it worked extremely well also for polymers. So the advantage of that technique is that you don't actually have to find the chip, and you can just determine you can determine just from this energy minimization what the final chip thickness is. So that was two methods. In fact, in the published work we had 4 methods where we also considered the conditions of the interface. If you do consider the different conditions on the interface between the chip and the workpiece, you can of course measure input or output coefficient of friction depending on which way you want to go, and also input or output. What we found was necessary if we're considering the interface between the chip and the tool was the adhesion between the material. Okay? We found that friction on its own wasn't able to explain what we saw, so there must be an adhesion term. So it was actually the polymer was actually sticking to the tool, and we put that adhesion term in and got some quite interesting results. But it's not what I'm going to be talking about this morning. So we've got different ways that we can approach this. So these are the analytical expressions. So these are either from this energy minimization or the ability to find the specimen and measure. But you can set up these equations from an energy analysis, which is how we did it. They do validate via equilibrium. And what we're trying to do is we're trying to find the intercept of these plots to determine GC for the polymer. Now, another interesting thing is you can output the yield stress also from this analysis. So the intercept gives us GC, and the slope gives us a term from which we can determine the yield stress of the material. And what we always found actually for this polymer cutting work was that the yield stresses were high relative to the uniaxial yield stresses that we would measure in a separate test. So we surmised from that that we were actually having obviously the deformations are large, so we had a large amount of work or strain hardening in this material. So we rationalised the relatively high values of yield stress in those terms. So this was just to explain how the energy minimization process worked, leading to a different set of equations, but basically the fundamentals is the same of the approach, and what you're trying to do, you're trying to get that intercept at the zero thickness. So in our experiment, briefly because time is short, we have our instrumented tool. So here's our cutting tool. We define a rake angle. So in our experiments, we were able to vary the rake angle. Not that you needed to vary the rake angle, but it was interesting to see that the results were relatively independent of the rake angle within certain limits. So we varied the rake angle. We tended to fix a clearance angle. You drive the tool and remove slices of your polymer of varying thickness, and we used a piezoelectric crystal load cell to measure FC and FT during the experiment. And what you do, this is what it looks like. When we first did this on our testing machine, we found that the machine wasn't stiff enough, and our standard high-speed Instron basically flexed too much in this direction to control. Remember, we're trying to control thickness, cut thicknesses down to about 25 microns. So you haven't got to have too much compliance in this to generate that sort of order of magnitude of wobble down at the specimen. So we moved to a very much stiffer system. So this is another machine we had in our lab, so much stiffer, and indeed we also put a guide on to stop any rotation. So that's something you needed to take into account. But what you can see that this is our tool here. So the rake angle, and you can see the clearance angle, the top tip of the tool. And then this is our workpiece. So our workpiece is clamped in the material, and basically we bring it down and we take a slice, and then we increment and take another slice, etc. So we can measure the force, cutting force, and the transverse force on the polymer, and we can convert that using our energy analysis to the sort of plot that we want, where we look at an intercept and a gradient. So for this particular polymer, so we're measuring about 0.6 of a kilojoule per meter squared for the energy release rate, and we measured in this case 91 megapascal for the yield stress. That's a relatively high. We know that was around about a factor of 2 on yield stress. So there's a lot of work hardening, strain hardening taking place in this. We tended to find the values were quite comparable to when we were using materials that we could validate via LEFM, quite comparable to the values that we got with LEFM. This was for a second polymer. We can see depth of cut against the cutting force and transverse force here. We convert that with our energy analysis, and we can see relatively nicely correlated data, giving us an intercept from which we deduce our energy release rate, and the slope, we get our yield stress. So really just to sum up on the polymer cutting idea of measuring G, so the technique is best used for ductile fracture. If the material is behaving in a brittle manner, you tend to get chattering. So what tends to happen is you get instabilities of the material ahead of the cutting tool, which just makes the analysis quite tricky. Rather than having a nice, smooth, steady state, you have very, very jerky, unstable. So it works best, therefore it does work best actually when the materials fail the LEFM criteria, which is, I guess, partly exactly the point for doing it. It has good repeatability and reproducibility when compared with standard techniques, and also with other labs running. So we had a number of different labs performing these tests. We got pretty good reproducibility. So, and I've mentioned the yield stress, but it does require non-standard apparatus. So that's obviously a drawback if you want to do these sort of experiments. In fact, someone now working in my lab did his PhD in Sweden, and he, in fact, presented his data at the last ECF meeting. Oh, actually, no, it was the last TC4 conference meeting, actually, where they were using an instrumented microtome. So you can get microtomes, particularly second-hand microtomes, quite cheaply. You possibly don't want to buy a state-of-the-art microtome, which is costing you hundreds of thousands of pounds and do these sort of experiments on. But you can get these. We picked up one for about $5,000, and we've used that. We've been using that in our lab for our broaching work. So these are not when you compare to the cost of new test machines, for example, these are not outrageous costs. You can set these systems up, and in that case, he was using biological materials and using this instrumented microtome to cut even thinner slices than we've been able to do. And of course, you have this notion, if you cut a very, very thin slice, so I talked about 25 microns, but he was cutting sub-micron slices. What does that mean if you're cutting a sub-micron slice? Are we approaching the true surface work? Okay, or is this something else? I mean, there's an issue here if you're cutting very, very thin materials, what you're measuring and what it means. For our work, we were the 25. Obviously we're engineers. We don't think too much below 25 microns, but in principle you could do. You could go to very, very thin slices and think about what it means. Okay. I think this is a good time for a break, Mr. Chairman. So we're going to have a break. How long do you want to break? Just 5 minutes? Stretch of the legs? And then we finish off, try and finish by 11. Okay, good. Okay, so should we start at 15:15? Okay. Okay, we're going to try and make a restart because we're going to try and be finished for around about 11 o'clock. So that we're ready for Professor Banksteel's after the tea break. Okay, so in the last session, I was talking mainly about polymer fracture and some of the issues with respect to measuring G1C in those systems. Some of the limitations and current problems we're having with the J, and some alternative ways of doing it by cutting. And what I want to talk about now is more related to composites. So are any of you working with composite materials? There's a quick show of hands. So I've counted 2 of you. Okay. Oh, 3. Sorry, I didn't notice you there. Okay, so 3 of you. Okay. So so apologies to those of you who are not specifically interested in what happens in a composite material. But as I mentioned in the earlier bit, when it comes to composites, of course the mechanical properties, many of the mechanical properties are dominated by the presence of high stiffness, high modulus fibers. Okay? And therefore, what happens in the material, for example, in between the fibers and controlling those fiber directions is obviously an important thing. So when we're thinking about fracture, we're thinking about specifically the different modes. So here, mode 1 and mode 2 is important for the reasons we've talked about. And of course, in a generalized situation, there's no reason why you would have pure loading on a crack. So you would more likely have a mixture of 1 and 2 and maybe a bit of 3, and the overall situation will be quite complex, as with the fracture mechanisms. So a really good way of analysing fracture in these problems was put forward by Gordon Williams in the 1980s, and he developed a generalised way of identifying and really establishing what the situation was with a crack in a laminate material, where you have only considered the loading on the global loading on the material. Okay, so the important thing of this analysis is that it was a global analysis and worked on the basis of bending moments. So, for example, for any crack in the system, you would have applied moments M1 and M2 at one end, M1 at the other end, and just on the basis of those applied moments, you could determine what was happening with respect to the crack at the crack tip. So you determine energy release rates based upon global parameters. And that was quite encouraging because obviously many of the analyses look at the details of what's happening at the crack tip. So you get into the K field and you get into the size of that and the specific stress displacement profile, stress crack length profile at the crack tip, and you build into lots of complexity. So what was quite appealing about this technique, this global analysis, was you simply needed to know what was happening away from the crack, and you determine the global energy release rates. And of course, the definition of G is the rate of change of the external work with respect to crack length minus the strain energy with respect to crack length. So, of course, if you don't have kinetic and other dissipated energy terms, you can determine your energy release rate. And that was come down through the bending moments. And this was used to derive a whole set of equations for mode 1, for mode 2, and for mixed mode fracture in these laminates. So, of course, this type of approach has been enormously useful for people working with composites, and probably the most frequently manufactured composite specimen is called the double cantilever beam specimen. We show it schematically here, where we embed the defect into the material during the manufacture. So unlike a block of polymer or metal where you're going to have a solid block you machined out and then you introduce a crack, what happens with these specimens is we think about the crack during the manufacture, because we don't want to be doing any machining of these relatively brittle materials with carbon fibers, for example, or glass fibers. We want the crack in there to start with. So we embed typically, it says aluminium foil in here, but that was used originally. What we tend to do is embed a sheet of PTFE film in between the two laminate layers on the mid-plane of the specimen whilst we make it. Then we cut the specimens out, and you can attach end blocks, and you've got a fracture specimen with a ready-made crack in the middle. And this is how it's realized. This is a test specimen on the right on our Instron machine being pulled apart from its initial crack length. And of course you can draw lines on the side of the specimen, and you can monitor the crack length versus load versus deflection. And schematically, if the specimen has carbon fibers, for example, in the longitudinal direction, the system is highly linear elastic, and you can see very nice linear elastic loading, unloading profiles from the specimen, from which you can very accurately determine the energy dissipated to grow a crack through a unit distance. So it's a very nice test. And you would think that there would be absolutely no problems with it. Of course, that is always not the case. The fracture parameter can be measured via simple beam theory. I won't go through all the details of it, but we assume, for example, a cantilever beam is built in perfectly at the crack tip. This is assumption number one. And then we can derive an expression for the compliance of that based upon beam theory. And then if we know the compliance, we can determine the rate of change of compliance with crack length, which is that critical parameter you need for the Irwin-Keyes fracture mechanics expression to determine an energy release rate. So we can easily determine an energy release rate based upon our experimental data from such a test. What you do if you use that simple approach, of course, is that you find a number of anomalies in the data. So something fairly early on was telling us that the assumptions we'd made were not correct in this case. So the corrected beam theory, which was built into that work that Gordon Williams talked about, was really to recognize what was wrong with the simple beam theory. Of course, a number of things were wrong, but the most critical thing was wrong was that assumption that the specimen was built in at the crack tip. Okay? Because the specimen is not built in at the crack tip. The specimen is free to displace and rotate at the crack tip. So that had to be taken into account. That's particularly true with the relatively low transverse modulus of the materials that we're talking about. Obviously, these sort of highly anisotropic composite materials can have, for example, a modulus along the length of the specimen of, for example, 150 gigapascals, but the two transverse directions, the modulus may be between 5 and 7 gigapascals. So they're very, very much lower. And of course, it's that vertical transverse direction which is leading to the shear deflection at the crack tip. So that's where a major error comes in if you don't take that into account. So that built-in condition had to be dealt with. Another couple of inadequacies in that basic method was, first of all, these arms can be relatively compliant. It's not that the material's not stiff, but it can be relatively thin amount of material, maybe 1.5 millimeter arm thickness. So you get relatively large curvature on these specimens when you test them, and that can lead to a shortening of the moment arm. If we start off with a horizontal length, when the beam is fully bent, maybe the horizontal length has shortened significantly, and of course we're measuring in the standard analysis, we're measuring the bending moment as force multiplied by horizontal length. That's what we should be doing. What we actually put in is force multiplied by crack length, which is the curved distance along the specimen. So that's an issue. The other thing that goes wrong, of course, is we have to physically test these specimens. We have to bond rigid end blocks onto the end of the specimen, which locally stiffens them. So there are a number of things that we've got to take into account to get that working. But a convenient way of dealing with the built-in condition was the notion to consider a slightly longer crack than you actually had. So a crack length correction term comes into the analysis. So this is the standard compliance equation based upon simple beam theory, modified by a slightly longer crack length. And that slightly longer, the idea about this slightly longer crack length is that although the condition is not perfectly built in at the crack tip, at a condition a certain distance ahead of the crack tip, it is perfectly built in. So you can make that modification to the analysis. If you can easily determine that, then it's useful. And of course, it is quite easy to determine it because from our experimental data, we can determine the compliance. And what we've effectively done here is we've just linearized that equation with respect to A plus this correction term, which is a parameter chi multiplied by the thickness of the specimen arm h. So this correction term is a length correction term, and it's that physical distance ahead of the crack tip that we have to move to get to our built-in condition. So it works quite nicely. Physically, this is what's happening on the experiment. You're looking at the compliance to the 1/3 against crack length. And of course, if simple beam theory was spot on, the data that you measure in the experiment would go through zero. And you can see that they don't. They go through an offset, and that offset is that correction term. So this was a nice fix for the experimental data. It was built into the standard for measuring G1C in composites, and it's been used very widely. And it solved those many of those issues that we talked about. So you can build these corrected beam theory versions for G1C. So here we have our fix for the built-in condition. Here we have our fix for this was simply a way of compensating for this curvature of the beam via a correction factor, and also a fix for the compliance of the beam caused by bonding on the load block. So these methods all were quite straightforward to apply and have been very widely used in the community. So people studying composite materials have used these, and it's probably one of the most commonly used experiments. This just would show how you use for example, if you take a range of composite materials, the matrix of the material is shown here. So these were all carbon fiber composites, but this one had a a relatively brittle behaving epoxy matrix. This one a tougher thermoplastic polyether ether ketone or PEEK matrix, or a polyether sulfone matrix. And you can see that you can measure, each one is highly linear elastic, but each one basically has different critical loads and different load displacement behavior, indicative of the different toughnesses of these different systems. And of course what you would expect there is that the higher the load and displacement, the more energy you're dissipating and the higher the value of G1C. So what was a complication with this experiment? So there were a number of them. Possibly one of the most significant complications was the getting back to the initial condition. It's a little bit analogous to our notching problem, but how do you start the crack off? And of course, one of the things that you have to make sure when you develop a fraction mechanics experiment, a specimen, is that you're not introducing an artifact into the behavior. So when we mould in our sheet of PTFE film at the mid-plane of the composite, are we changing the material at all? Is there any other change to the material that wouldn't have been there otherwise? And of course the answer to that is it depends upon the thickness of the film that you embed. And this diagram explains what I mean actually. So this was some micrographs taken by polishing the side of the specimen at the end of the insert material. And what it showed quite nicely is that if you use a single layer of film, you can see the extent to which the fibres are displaced around the film. So of course the thicker the film that you embed, the more fibre displacement you have and the more potential you have for a what's described as a resin-rich pocket to form at the crack tip. Okay? So this is a problem because if we embed a film into the material and by embedding the film in we displace the fibres, we have a big resin-rich pocket ahead of our initial crack. What we would then expect is the fracture toughness to be that of the resin, not that of the composite, when we get our initiation value. Okay, so we could have suspect initiation values. Now, does this matter? So this again depends upon our philosophy. So in the ESIS TC4 group, we've always had the philosophy that we're interested in crack initiation, but we're also interested in propagation. We want the full information about the experiment. We want to know how it initiates. We want to know how the fracture resistance changes as the crack grows. Okay? So we want that R curve. That's not necessarily universal. So if you take the much of the work that was done in the US and the ASTM methodology, it was very much the case of the initiation is the only important point. The rest of it is subject to specimen dependence. Now that's true partly in as much as, of course, if we have a strong R curve, so if we have an increase in fracture resistance after crack initiation, which certainly can occur with these materials, then what you're measuring is, for example, the proportion of the extra energy being dissipated by mechanisms such as fibre bridging. And fibre bridging is somewhat specimen dependent, okay? But you have to make that distinction, and if you are interested in the initiation value only, and if you're interested in the initiation and the propagation value, you've got to actually have confidence in it. You've got to try and get it right. So what could be done about this? Well, of course, the very straightforward thing would be done to put into the standard a maximum thickness of film that can be accommodated. So don't use an initial film of greater than, and the standard says 13 microns, okay? So of course if you put something into a standard, only a certain proportion of anyone will read it, unfortunately, so you get lots of data out there where people put in 100 micron film. And you see it in research papers all over. You think there's a problem, there's 100 micron film, you can see, you know what's happened, okay? They haven't followed the standard, but if you have a thick film in there, you can disrupt these experiments quite badly. So you need a sort of a belt and braces approach to this. You say, well, okay, you might not have the right film thickness, but is there anything else you can do? And of course, the anything else you can do is pre-crack. You can say, well, okay, we can actually take... Is there a question?
Yes, can you explain the
Explain better the figure. Yeah. So explaining better the figure. So what you can't really see the film, but you can see the matrix. So this, what you see as black, is the matrix. Okay. And what you see as light, in this case, was the fibres. So here you can see the tip here is distinctly thinner than the tip around about here. So the embedded polymer film, by being thicker, has created this block of polymer around the crack tip. Yeah, okay. So the thinner you make that film, the less matrix you're going to have around the end of the crack. Okay, sorry for that not being too clear. So you can, of course, control the thickness, but the other thing, of course, you can do is pre-crack. So into the standard methodology, we put in the clause that you have to grow the crack ahead of the film that you embed. So you have a pre-cracking step, and then you unload, and then you reload from your pre-crack. So if you had a situation where your film was too thick for whatever reason, then you would have a way of having grown a more natural crack away from that embedded defect. So that was if you like, a belt and braces approach built into the standard to try and avoid that problem. There are other problems that can occur with these experiments, which we run into periodically. And you can see in this case, this is a unidirectional glass fibre epoxy composite. So you can see here the initial crack. So what's happened in this case is that we're getting extra cracks occurring in the composite arms. So we're getting, what this would lead to, of course, is extensive fibre bridging in the specimen. So the crack is sometimes it's bifurcating, or you're getting micro cracking of the composite above and below the main crack. Okay, so the validity of LEFM is getting more strained significantly in these sort of situations. Of course, other situations where you just have maybe non-UD materials. So obviously we're interested in laminate systems where we have 0-90 degree, we have general multi-directional fibre reinforcement, and of course you have many different types of crack propagation and mechanism. So this can lead to fairly complicated crack shapes. You can see this sort of sinusoidal type of fracture where the fracture is actually going up and below basically toes of fibres that are going transverse across the specimen. So you're getting a distorted fibre fracture shape, and of course this is also leading to fibre bridging. Of course, if you then do a series of tests where you look at what we did in this work is we actually correlated the correction term that we had in these data. So this from our compliance to the 1/3 against crack length data, we looked at that correction term as a function of the modulus that also comes out of the analysis. And what we found in our work for a range of materials is systematic variations in these parameters. So what were these systematic variations telling us? Well, they were telling us, we think, that when you do these experiments, typically the PhD student or the researcher is looking at the side of the specimen with a microscope and you're measuring the crack length. Either a microscope or a camera is being used and you're recording that information. If you have a very well behaved fracture, it's very easy, relatively easy, to see where the crack tip is. And the more complicated the fracture gets, the more difficult it becomes to actually see where the crack is, and you have systematic problem here in interpreting where the crack is. This is not just a random variation, it's a systematic variation, particularly when you have what I'll describe as discontinuous growth ahead of the main crack. And you need a way of dealing with that. So if someone in the lab is just measuring the extent of a crack, and you haven't noticed that ahead of the crack there's quite a lot of stuff going on, but it's discontinuous, it hasn't met up. What do you measure? So typically one will measure the continuous crack, and you would then systematically underestimate the crack length. And that systematic crack length underestimation has knock-on effects on the analysis right the way through. So this really is just an indicator of what's happening across a range of specimens. So, for example, these data here were for some glass fibre reinforced PMMA. So these data here, glass fibre reinforced PMMA. So that was one batch of specimens. And across that one batch of specimens, we had this large systematic variation in the fracture parameters. So obviously cause for concern. One has to inspect these data carefully when they stop behaving in the classic linear elastic manner that we anticipate. So that's a very nice time to actually just now think of mode 2 fracture, because how we obtain mode 2, so remember what we mean by our mode 2 fracture. So rather than having tensile opening mode, which is the easiest way to propagate a crack, we're applying in-plane shear. So we're trying to grow the crack in this shear mode, okay? And the best way of obtaining the in-plane shear mode is via bending. So classically, we'll either have, you can see all of the different approaches shown by this slide involve having a cracked specimen, a crack at one end, and then the specimen is bent. So you put it into a bending test. So that's schematically what's happening. The ASTM group have preferred a 3-point bend version of this, which is then described as the end-notched flexure test. It's end-notched, you can see, and it's a flexure test, whereas the ESIS group has preferred the ELS version of this experiment, which stands for the end-loaded split. And this is a cantilever clamped at one end. So you can see there are complications of the clamp. But the advantage of the clamped system, actually, is that it has better stability profile than the free system here. So the free system, the ENF system, tends to suffer from more instability. So if you're performing this experiment, it's more likely that the crack will go unstable and will run straight to the centre of the sample following crack initiation. Does that matter? Well, it does if you like to measure R curves, if you like to know the resistance to initiation and propagation. We think that that gives us more information. So there's been a policy to favour the lower ELS type of specimen to perform these experiments. So this is how we do it. We have a calibrated end-loaded split experiment here. So what do I mean? I'll explain what I mean by calibrated in a minute. But just to explain the basic methodology, we have a specimen which has an embedded defect. So this is our inserted PTFE strip in the centre of the specimen at one end. It's put into a clamp and clamped. It's important that the clamp is on a free sliding roller trolley, because otherwise you introduce horizontal forces during the experiment. So the experiment only wants vertical forces, so you allow this to slide freely. So this is realised in our lab. This is our free sliding fixture. This is our clamp. This is our loading port here. This connects to the tensile testing machine. It pulls on it. And this is the schematic, well, so it's a photograph of the crack growing in mode 2. So you can see that the crack grows, that the lines shear. And if you look very closely ahead of the crack, you can see typically a range of what we describe as micro cracks. So ahead of a main crack where you've got continuous delamination, you can have some discontinuous delamination. Now, when I'm talking about systematic defects, here's another example of a systematic defect. How do you approach this? How do you write into a standard methodology what should be measured? So when we first approached this problem, we said, oh, we just need to look more closely. So you buy a high magnification camera, and you stick the high magnification camera in, and you get a completely different answer. But when you're looking at high magnification, sometimes you completely miss what's happening because you can't see the wood for the trees because you're too focused in on one thing, and you miss what's going on 5 millimeters down the sample. So it was a sort of it was a quick fix, but it didn't work. So what we decided to do actually was to abandon the whole concept of measuring crack length in these experiments and move to a compliance-based way of approaching this. And of course, if you base crack length from compliance, basically what you're saying is you're going to measure an effective crack length based upon the compliance of the specimen, based upon your, for example, your corrected beam theory. So you would assume a particular theory, and then you're basically going to say, well, we're going to apply the compliance theory to that, and we're going to take out the crack length. That would be an effective crack length. The problem we had with this approach was that we were using a clamp, and one clamp, point number one is that whenever you clamp a specimen into a system like this, you might not do it repeatedly yourself. And secondly, if you're trying to measure the reproducibility, i.e. one lab to another lab, they're going to have different clamps. And you're going to have lots of different effects on the compliance, which is very hard to rationalize. So what we had to build into the method is a way of calibrating the experiment. So whenever someone is performing these sorts of experiments in their lab, what they do is they calibrate their apparatus on what we described as an inverse ELS clamp calibration. So what you do is you take a specimen which can be uncracked, or you can have it in the reverse format, so the crack is held completely in the clamp, which does then mean you can subsequently reverse it and do a fracture experiment on it. But you do this and you effectively measure the compliance of the system for different clamp lengths, and you measure, this is analogous to what I was talking about in mode 1, where we were measuring that chi-H correction term. It's like we're doing this now, but for the clamp. We measure an offset here which calibrates our clamp. And if you ask different labs to do this clamp calibration, this fixes the issue of clamp variability. So we found in our round-robin experiments in ESIS TC4, this was a good fix to the problem. And of course you can then go on and you can determine your, in this case, G2C values, because we're now in the in-plane shear mode. You can use simple beam theory, experimental compliance, and all this newly proposed effective crack length method. Interestingly, lots of papers in the literature use this approach and argue it's the most accurate approach because you're using compliance. Now the problem with that sort of compliance approach is that it's heavily dependent upon the crack length. So it's actually the worst one to use. So we built this into the standard methodology. We think it's the best way of doing it. Of course, ASTM have their end-notch flexure experiment. We have our ELS experiment, but both fairly widely used. So we're able to develop these sorts of R curves, so these resistance curves. So we look at how much as a crack grows, what happens to the fracture resistance, and just different ways of calculating the value. But this was our favoured approach, where we used the effective crack length values. It's probably worth noting with this experiment, we can see that the mode 2 fracture resistance is about 4 times the mode 1 fracture resistance. Okay? So what we're saying here is that when we perform this fracture experiment in mode 2, we're dissipating approximately 4 times as much energy than when we load in mode 1. So it's interesting, why is that the case? What's happening to this extra energy? What's going on micromechanics-wise at the crack tip to dissipate so much more energy? So there's been quite a lot of work on this. I've just pulled in a few slides from a very nice summary presentation put together by Kevin O'Brien at NASA Langley, where he looked at, he did quite a nice study where he looked at the difference between G1 and G2C for a wide range of different composite materials, and found that for epoxy-based composite materials, these values of this multiplication from from 1 to 2 range from about 3 to about 12 or something like that. So it's quite a big range, but all of them were significantly tougher in mode 2. And of course, if you look at the micromechanics of what's happening at the crack tip, we looked at some inclined microcracks in an earlier slide, but here you can see the idea that you can have a head of a shear crack, you can have these extended microcracks extending into the material. So formation of tensile microcracks, and of course what then can happen is that the material in between the microcracks can shear yield. So it's sort of, there's an almost an analogy to the crazing mechanism of a polymer, where you can have lots of voids and you can have material forming fibrils in between. Of course, we're talking epoxy here, so we're not talking about crazing, we're not talking about fibrils, but we're just talking about shear failure of ligaments of material in between microcracks. And it's widely believed that, of course, it's this extra energy dissipation by the failure of these little shear ligaments that is causing the large increase in the fracture resistance.
But
Yes.
with the shear mode being applicable, the crack is still straight.
Okay, so it's a good point. So what's the direction of the crack? So the crack would, if this was not a composite material, the crack would want to veer off. Okay, so the crack would head off at approximately 45 degrees. So the fibres, either side of the plane where the initial defect has been put, are constraining the crack. So the crack has tried to go up, it hasn't been able to. So initially it'll stop. Stresses will rise, a stress distribution will form ahead of the crack tip, and then shear cracks will form at a certain distance ahead of the main crack via a shear lag mechanism. Okay? Now, interestingly, this is material dependent. So for relatively brittle materials, you get this extensive shear cracking ahead of the main crack. And what will then happen is the main crack sort of bumps along, picking up the discontinuous bits of material and shear yielding them as it goes forward. What will happen, oh yeah, and you can see, if you just look on the next slide, you can see what the fracture surface looks like if you actually look at the material after a mode 1 fracture and a mode 2 fracture. The basic idea is that if you have an epoxy material behaving in a relatively brittle manner, you have a relatively small plastic zone at the crack tip, dissipating a relatively small amount of energy. Now, in the mode 2 fracture, what you have is the extended region of microcracks, which subsequently shear yield. So what happens initially is that tension microcracks open up normal to the maximum principal stress. So there's a rotation of the stress field because we're talking about mode 2 fracture, shown by the schematic here. And then these tension microcracks open up, and they open up for a given length. What then happens is the crack will come along and join up these ligaments, dissipating the energy. So what's interesting is that it's material dependent. So if you go to a tougher system, like in this case we've replaced the epoxy matrix with a thermoplastic PEEK material. So this is now a much more ductile polymer and typically has a much higher mode 1 fracture energy. So if you then just basically make your material of this and you run a mode 1 crack in, so this is the mode 1 situation, but now we have the more ductile matrix. What we see happens there, first of all, is under mode 1 conditions, we have a larger plastic zone because the material is behaving in a tougher, more ductile fashion. What happens now in the mode 2, and this was an interesting question, because if this region of multiplication factor of about 3 to about 12 work for epoxies, should it work for tougher systems? It would be great if it did, because if you started with a material that was already 10 times the toughness of epoxy, what sort of toughness might you have in mode 2? So it was of interest to see that was never actually realised. And when you went to the tougher matrix material, in mode 2 it was never as tough as you expected it to be. And what they found, we found and other workers found as well, is that there was not so much difference between mode 1 and mode 2. And what this was put down to, so these were Kevin O'Brien's slides, but he basically put forward the notion that if you have a relatively large plastic zone here in mode 1, that stops the tensile microcrack mechanism actually kicking off. So you don't get the elevation, because of the extra ductility, you don't get the elevation of the stresses required to generate the tensile microcracks ahead of the main crack tip. So the mechanism, so the micromechanics of the process is different. So what actually happens, therefore, in the mode 2 situation is that simply the damaged zone rotates, but is around about the same volume or area in 2 dimensions if we're looking at it here. So you imagine a more or less similar total energy dissipation. In terms of mixed mode, of course, we're just talking about a combination of those 2 things. So you could add them together, and you wouldn't be too far off. The ways of introducing mode mix are many, but almost invariably involve bending again. But typically, rather than bending both arms at the cracked end in the same sense, you load them in different senses. Hence, you introduce mixed mode. The one that we've been developing at ESIS TC4 is the top one, where you simply load one of the arms but don't load the other. So the top arm is left unloaded, the bottom arm is loaded. Or it could be done the other way around, but that's the idea: one arm loaded arm and one loaded arm. And you devise a very simple mixed mode experiment which has a fixed ratio. So the ratio of mode 1 to mode 2 doesn't change as a function of the crack length. ASTM have standardized this one. This is described as the mixed mode bend experiment. The apparatus is more complicated, but it has the advantage that you can generate a complete failure locus, i.e. you can adjust the lever arms to get many different ratios of mode 1 to mode 2. So it's quite versatile. And there are other ways of doing it. I want to just very quickly show you our fixed ratio mixed mode experiment. There's a composite. The top arm is being loaded, the bottom arm is not loaded. The other end of the specimen is clamped in exactly the same way as we would clamp for mode 2. And we can get very nice, and we can also apply the effective crack length approach to that experiment. So it's not always necessary, but if you were going to more highly mode 2 end of the locus spectrum, it would be necessary. So we get very nice reproducible data, and this is the final result. You can get this sort of curve where we plot the mode 1 value against the mode 2 value, and you generate a 1-2 failure locus. So the mode 1 data falls up here, the mode 2 data falls down here, and our mixed mode value falls there. You might pragmatically want more data points. Using the ASTM mixed mode bend, you can fill in points along here. 3 points gives you a quick yardstick as to how the material is behaving in the 1-2 mode. So you can see for this one, we had a mode 2 fracture resistance of about 1400 and a mode 1 of somewhere between 300 and 400. So that was our sort of factor of 4 to 5 in this material, and you can see that our mixed mode value fell on that particular failure locus. I just want to make my final remarks about mixed mode fracture and partitioning, because does it matter really? We can we've measured mode 1 and we've measured mode 2, or we can do, and we can have a mixed mode. Is it always necessary to know for a given fracture energy how much is mode 1 and how much is mode 2? So there are, particularly if you're analysing engineering systems where you won't necessarily know and you'll have to try and work it out. And it's important to work it out for the very reason we see here, because we know that the mode 2 fracture resistance is so much higher than the mode 1 fracture resistance. So if we can't adequately partition a total energy release rate in a given system, we don't know what G values to ascribe to actually work out the toughness. So it can lead, so ultimately it just leads to higher degree of conservative design. If we don't know, we have to say, well, let's assume it's all mode 1 and we work with a lower value. Okay, well that's not great if you're trying to minimize the weight of a structure because you're trying to take material out. So there's been quite a lot of discussion about partitioning accurately, and this is a complicated subject, and I could talk for 2 hours on it. Fortunately for you guys, I'm not going to. But the takeaway point really is that if you need to partition any of these energy release rates accurately, it is unfortunately a material specific problem. And what partitioning strategy will work for one material won't necessarily work for the next one. So the way to rationalize it is that it depends upon the degree of damage at the crack tip. And what we found, and there's been some excellent recent work by, for example, the guys at Dublin, Conroy and Ivankovic, and working with also some of my colleagues at Imperial College, looked at quite a wide range of different materials. And it comes down to the degree of damage at the crack tip. So materials where you have a very small damage zone that are behaving in a brittle fashion, okay, to partition those energy release rates, it's best to use a local singular field approach. So you don't use a global analysis as proposed by Gordon Williams in that earlier work. You use this local field analysis proposed by Hutchinson and Suo and others. For example, Barry Davidson in the United States came up with a relatively similar partitioning scheme. So this is when you have relatively little damage and the size of the K field, so the size of that zone ahead of the crack tip, is the size of the K controlled field is larger than the damage zone. And that's when this partitioning scheme works well. Now, if you try and apply that partitioning scheme to a system where the damage zone is large, and the damage zone is much larger than the K-controlled zone, you get ridiculous values. It doesn't work. So if you've got a scheme where that is working, then, where you have the large damage zone, you're much better off with a global analysis. Okay? So big damage zone, global analysis, small damage zone, local singular field approach is best. So a pragmatic solution was actually put forward by these guys who said, well, actually, what we're going to use is we'll have some way of working out where we are between these two limits. If we're the local singular field approach and the global approach, imagine these as extremes in our fracture process. And we're somewhere in between in a real material. If we can devise a scheme for working out where we are, and they did this based upon cohesive zones, then you can work out this, if you like, your factor of singularity, which can range from 1 if you're completely singular to 0 if you're completely global. Okay? Once you've worked out this factor of singularity, you can use that to accurately partition using a semi-analytical approach. And we use that on a number of systems. It works well. So I guess the takeaway message is if you find yourself needing to partition into mode 1 and mode 2, first of all, know your material. Okay? Know how much damage you have at your crack tip, and then select your partitioning scheme accordingly. Okay? So no one scheme, i.e. singular or global, works for all materials. And that sort of clarified a lot of the confusing literature there's been over about the last sort of 20, 25 years on how best to partition. Because it's not always clear from a material whether it'll be singular or global. It's not intuitively obvious at all. You might think if the resin is, if the matrix of the material is brittle, it'll be singular. That might be wrong. because it depends not only on the toughness, it depends upon the other elastic properties of the system. So that is what I wanted to say about the partitioning. So in terms of outlook, just a final remark, because it's coffee time and we want to be ready for Professor Banks-Sills. In terms of polymer materials, so a main current challenge is to sort out our methodology for our J1C testing. So we know that our multiple specimen approach currently has a number of significant limitations. We're working on resolving those in collaboration with others. Anyone who's interested in joining the activity, do let me know, because there's lots to do, lots of good science and so forth to be had there. We're hoping for lots of stimulation at this conference with all of the excellent presentations we're going to hear on J. So we're waiting with bated breath for that. With composite laminates, and I've talked mainly about unidirectional systems, and of course there's a lot that needs to be done in terms of non-UD engineering laminates, lots of extra complexity that needs to be sorted out. The one above I skipped, but this is what to do about fatigue. So fatigue has been a major issue for polymers. In terms of polymer composites are extremely fatigue resistant. Okay, so the reason that they're used routinely in aircraft structure is because of their very excellent fatigue resistance compared to many metals. Okay, so they have excellent fatigue resistance. Okay, but understanding that fatigue resistance has been another challenge. Okay, so most of the ways that we analyse fatigue tend to be empirical. I mean, at the last ECF meeting, we honoured Paul Paris for his excellent work on using empirical methods to understand fatigue. Okay, and applying those to polymers and composites has been the obvious way that the community has followed. But there is a problem in that we really don't, at the moment, understand in a composite really how the crack grows, what's actually happening at the micromechanics level, and what's the true physics of the process. So a real proper physical model of fatigue in composites is really lacking, and that's really a major challenge for us all and those of us working in the area. So on that, I'm going to thank you for your attention. It's coffee break, and if anyone wants to discuss any things in particular, very happy to take your questions afterwards. Come up and chat to me over coffee. Thanks for your attention.